n bracket psi m psi n. Now, we assumed at the beginning here that these two eigenvalues are different, right? So now if I subtract both sides by the right-hand side, I'll get lambda m minus lambda n times this equals 0. Okay, I get this equation. But lambda m and lambda n are assumed different. Therefore, this is not 0. Okay, because lambda m is not equal to lambda n, and therefore this term must be 0. And there's our proof. Okay. So then the bracket of psi m psi n is 0. In other words, these two eigenfunctions are orthogonal, and there it is. Okay, nice. So, so in other words, summarising a bit, we've gone both ways. We're talking about the general context of eigenequations, which are really important for quantum mechanics. It's a really fundamental tool that you can go very far with and calculate all kinds of different stuff with. You think of it, you have an observable, some measurable physical quantity. You want to know what its possible, discrete, quantized, allowed, measurable values are. Well, you just solve, as long as you got the right operator, you just solve the eigenequation, and your allowed measured values are your eigenvalues. Right? That's sort of really important. Okay, so and we place a bit of revision here. We put restrictions on the nature of the eigenvalues. They have to be real valued. They have to be real numbers, and we wanted the eigenfunctions to be orthonormal, because then we could expand any arbitrary wave function as a weighted sum of these orthonormal eigenfunctions, and that gave us our probability amplitude, the C's, the coefficients, in terms of the superposition, the sum of Ci psi I. Remember that? I've done that several times. Okay, so those two conditions, that the lambdas, the eigenvalues have to be real, and the eigenfunctions have to be orthonormal. With those two, we then concluded that the eigenequations operator must be Hermitian. Okay. Now we can go the other way, and we've just finished proving it now, that if your eigenequation operator, say a hat, if it is Hermitian, then going the opposite direction, the eigenvalues are real and the eigenfunctions are orthonormal. Okay? And we will use those. Now that's very general discussion for a general eigenequation for any observable that we like. Let's say observable big A, whose corresponding quantum mechanical operator, Hermitian operator, is a hat. Okay. Well, let's so that's the general discussion. So let's be a bit more concrete and have a look at some candidate quantum mechanical operators and see if or not they are Hermitian. Okay. So here are two closely related candidates as operators. They're obviously operators, just telling you to differentiate and multiply by I. In this case, simply just differentiate with respect to x. Okay. And the question is, this operator, is it a Hermitian operator? In other words, is I dBdx Hermitian? And a similar question for here, but there's no I. The only difference is this I is missing here. So is dBdx Hermitian? Okay. Now, we're assuming this is an operator. We call it A, big A, so A hat, right? The hat makes it an operator. Now, from the previous equation, starred circle, which was here, right? This is the definition that operator. God, I keep doing that. that this operator A is Hermitian. That's the definition, right? And this is just a rewriting, an alternative, the Dirac bracket notation, but it's just saying the same thing as this. Okay, so from this, we can, and we substitute A being I d dx, so we substitute that in here. So so this here is just this starred equation, right? Now this star and this star, don't confuse it. This is just an ID. I mean, I could put a number, I could put anything here. It's just this is just a mark to identify this equation. That's all it is. Right? Don't be confused. Right. So taking that, and you get this. Right? So the left-hand side is this one, and the right-hand side here is that one. Okay. Now we can rewrite this. So you've got your conjugate here. So that's just telling you change this I to minus I. So you've done that, and it's just a constant. So bring it outside the integral. So you've got minus I here from I starred, I conjugate, same thing. D phi star dx. X is assumed to be real. So okay. So in other words, you've got this equals that. Right? Now just shelve that for a moment. Put that on the shelf. We'll come back to it in a moment. Now, can you see that this is 0? Imagine you have like integral dx. Well, it's just x. The integral of 1 dx is just x. Well, in this case, d of this will just be this evaluated at the limits, which will be assuming minus infinity and infinity, right? But they're physical wave functions assume, and therefore they drop off to 0 as x goes to the limit. So this integral here is 0. Right? I hope you find that plausible. So just from general calculus and basic physics assumptions like this, that these wave functions drop off to 0 as x goes very large, either way, plus or minus. Now, what is this? You can rewrite this. Well, phi and psi are functions of x, so you can rewrite this just from calculus, high school calculus. So you can rewrite this as this, right? D that dx dx, okay? And then if you differentiate a product, if you differentiate uv, you get u v dx plus v du dx. So that's of that form. But this equals 0, that equals 0, therefore this equals 0, therefore the integral of this is equal to minus the integral of that. Right? And that's true in general, right? Whatever these are. But the integral of this equaling minus the integral of that is just this, right? Yeah. Phi star d psi by dx, there it is here. Okay. And here you've got psi d phi star dx, psi d phi star dx, and the minus. So therefore this plus this, if you bring this over to here, will be 0. And that means this and this are equal. Right? But what is this? Well, it's the condition for this. I mean, it's the hermeticity condition. So in other words, the A hat here, which we use for this, satisfies the condition for hermeticity, right? So in other words, I d dx is Hermitian. So give it a tick. That operator I d dx is Hermitian. Okay. Now I've run out of board for this session. So I'll just continue straight on in the next session, and we will prove. I'll jump ahead a little bit and just tell you what the result is. this operator here, and it's only slightly different from this one, and in that is that the I, the square root of minus 1, the I here is missing. But that's critical, and we will show next session. This operator, dvdx, is not Hermitian. Okay, so I'll just carry straight on.